On a scorching July morning in 2003, the humid air above Cecil Field hung heavy and still. Cecil Field, once a bustling naval air station on the eastern edge of Jacksonville, Florida, had fallen quiet years before, its runways now serving a different purpose. But on this particular day, something extraordinary was about to happen. Two small supersonic jet aircraft sat on the tarmac, their engines beginning to spool up, preparing for a journey that would take them across the entire continental United States. Though both aircraft had been built by the Northrop Corporation and shared a common design heritage, a casual observer might have struggled to recognize them as relatives at first glance. One was a sleek Northrop T-38 Talon, a two-seat aircraft that had faithfully served as the United States Air Force's advanced trainer since the early 1960s. The other had started life as an F-5E Tiger II, one of more than 2,000 Northrop F-5 fighters that had equipped air forces around the world with a remarkably cost-effective, high-performance combat and reconnaissance platform. But this particular F-5E no longer looked quite like a fighter jet. With what appeared to be an elongated pouch hanging beneath its chin, the aircraft bore an uncanny resemblance to an oversized pelican. The modification wasn't cosmetic. It represented years of research, decades of theory, and the culmination of efforts that trace their roots back to the very dawn of supersonic flight. The pilots climbing into their cockpits that morning understood they were about to fly something historic. This wasn't a classified military project shrouded in secrecy, though it was funded by DARPA, the Defense Advanced Research Projects Agency. The modified F-5E was the centerpiece of something called the Shaped Sonic Boom Demonstration, often referred to simply as SSBD. It was part of a broader program known as the Quiet Supersonic Platform, or QSP. The goal was audacious, perhaps even quixotic to some skeptics. These engineers and test pilots were attempting to do something that many believed impossible. They were trying to tame the sonic boom. For decades, the thunderous crack of a sonic boom had been both a symbol of technological achievement and a source of public nuisance. When an aircraft breaks the sound barrier, the shock waves it creates coalesce into a distinctive N-shaped pressure wave that strikes the ground with startling force. To those on the receiving end, it sounds like an explosion. A thunderclap that rattles windows, startles animals, and in enough cases had even caused structural damage to buildings. The sonic boom had become such a problem that by the early 1970s, the Federal Aviation Administration and Congress had banned supersonic flight over land in the United States. Similar restrictions existed in most developed nations. The dream of routine supersonic commercial flight across continents died before it could truly begin, killed not by engineering limitations, but by the relentless physics of shockwaves propagating through the atmosphere. But what if the boom itself could be shaped? What if, instead of that sharp, startling crack, a supersonic aircraft could produce something gentler, something that might be no more disturbing than distant thunder? Theoretical work dating back to the 1960s suggested it might be possible. Researchers like A.R. Seabass, Arkansas. George and Christine Darden had developed mathematical frameworks showing that careful shaping of an aircraft's fuselage could modify the pressure signature of the boom as it traveled through the atmosphere. But theory is one thing. Proving it with an actual aircraft flying through real atmospheric conditions is something else entirely. That's what made the shaped sonic boom demonstration so important. For the first time in aviation history, engineers were going to take a real airplane, modify it according to sonic boom minimization principles, and prove that shaped booms could persist all the way from cruise altitude to the ground. The pelican-nosed F-5E sitting on the Cecil Field tarmac represented the physical embodiment of decades of computational fluid dynamics, wind tunnel testing, and careful engineering. In the coming weeks and months, this aircraft would generate sonic booms over Edwards Air Force Base in California, booms that would be meticulously measured by arrays of sensors on the ground, microphones mounted on sailplanes gliding silently beneath the flight path, and instruments aboard a specially equipped NASA F-15B chase plane flying in close formation. The story of how this project came together involves a fascinating cast of characters. There were veteran test pilots who had flown combat missions over Vietnam, engineers who had spent their entire careers understanding the complex mathematics of supersonic flow, researchers at NASA's Langley and Dryden facilities who had been collecting sonic boom data since the early days of the space age, corporate teams from Northrop Grumman, Boeing, Lockheed Martin, and Gulfstream who put competitive rivalries aside to collaborate on solving one of aeronautics' most persistent challenges. And perhaps most remarkably, there was an old Navy F-5E fighter jet that had spent years being thrown around the sky in adversary training missions, simulating Soviet tactics for American fighter pilots learning aerial combat. This particular F-5E had accumulated thousands of flight hours performing aggressive maneuvers at Naval Air Station Fallon in Nevada, where the Navy's famous Top Gun program had relocated in the mid-1990s. The aircraft had been flown hard, pushed to its limits, and had earned its retirement from frontline service. But instead of ending up in a boneyard or museum, this tired fighter was about to receive a new nose and a new mission. It would become a flying laboratory, a test bed for technology that could one day make supersonic commercial aviation over land a practical reality. The journey to this point hadn't been straightforward. The path from theoretical research to actual flight testing had been filled with challenges, setbacks, dead ends, and breakthrough moments. Engineers had initially considered using remotely piloted vehicles, specifically the Ryan BQM-34E Firebee, a target drone that had served the military for decades. They had even acquired surplus Firebee components from Point Mugu Naval Air Weapons Station, trucking them to Northrop Grumman facilities in El Segundo, California. But analysis revealed problems. The Firebee's airframe might not have been long enough to demonstrate a definitive shaped boom signature. Its inlet design created shockwave complications, and when technicians inspected the Firebee parts that had been stored outdoors in salty coastal air, they found the components had deteriorated significantly since the mid-1990s. So the team turned to the F-5E. It was a brilliant choice for reasons that went beyond simple availability. The F-5 family had been designed from the ground up for lightweight performance and ease of maintenance. Its relatively long, slender fuselage, with engine inlets located farther back than most fighters, minimized interference from secondary shock waves. Its high fineness ratio and blended canopy contributed to favorable sonic boom characteristics. And crucially, Northrop Grumman had already developed longer-nosed variants of the F-5 for two-seat trainers and reconnaissance versions, providing both the engineering data and manufacturing experience needed to create a properly shaped nose extension. What we're about to explore is the complete story of the Shaped Sonic Boom Demonstration project. We'll trace the history of sonic boom research from the very first supersonic flights. We'll meet the engineers, test pilots, and scientists who made the SSBD possible. We'll follow the technical challenges they overcame, from installing GPS equipment in cramped cockpits to conducting unprecedented in-flight measurements of shockwave patterns. We'll experience the tension of test flights where years of work came down to whether sensors would capture clean data during brief supersonic passes. And we'll understand why this project, which might seem like an obscure piece of aerospace history, actually represents a critical stepping stone toward a future where supersonic travel could become as routine as subsonic flight is today. The sonic boom problem had haunted supersonic aviation from its very beginning. To understand why the Shaped Sonic Boom demonstration mattered so much, we need to understand where sonic booms come from and why they became such an intractable problem for aircraft designers. The Sonic Boom Challenge: Thunder from the Skies. The sound barrier wasn't just a metaphor. In the 1940s, as aircraft pushed toward the speed of sound, strange and dangerous things began to happen. Control surfaces would become ineffective or reverse their effects. Wings would buffet violently. Some aircraft broke apart in flight. Engineers didn't fully understand the complex aerodynamic phenomena occurring as aircraft approached Mach 1, where the local flow over parts of the airframe became supersonic, even though the plane as a whole was still flying subsonically. This transonic regime was genuinely dangerous, shrouded in mystery and incomplete theory. On October 14, 1947, Captain Charles Yeager, better known as Chuck Yeager, climbed aboard a bright orange Bell X-1 rocket plane suspended beneath a B-29 bomber at Muroc Army Airfield in California, later renamed Edwards Air Force Base. The X-1 had been designed as a pure research vehicle, built with one purpose: to explore what happened at and beyond the speed of sound. Its shape was inspired by a .50 caliber machine gun bullet, a projectile known to fly supersonically without breaking up. When Yeager lit the X-1's rocket motor and pushed through Mach 1.06 that morning, the shockwave from his aircraft propagated down to the desert floor as a distinctive thunderclap. That sound, rolling across Rogers Dry Lake, was the first sonic boom deliberately produced by a manned aircraft in controlled flight. It marked the beginning of a new era in aviation, but also the beginning of a problem that would plague supersonic flight for decades. The sonic boom wasn't an anomaly or a temporary phenomenon that occurred only at the moment of breaking the sound barrier. As Yeager and subsequent test pilots discovered, the boom was continuous. As long as an aircraft flew faster than sound, it generated shockwaves that propagated through the atmosphere, and anyone positioned in the path of those shockwaves would hear and feel the boom. The boom didn't emanate in all directions like sound from a conventional source. Instead, it formed a conical region behind the aircraft, like the wake behind a boat. As the aircraft moved, this cone of shockwaves swept across the ground, creating what researchers would come to call a boom carpet. For test flights over remote desert locations like Edwards Air Force Base, sonic booms were more curiosity than crisis. But as supersonic aircraft became more common, particularly with the introduction of supersonic fighters in the 1950s, the booms started affecting civilian populations. In June 1956, just 9 years after Yeager's historic flight, an Air Force pilot flying an F-100 Super Sabre produced a sonic boom over Los Angeles during a military demonstration. The boom shattered windows and terrified residents who had no warning of what was coming. The incident sparked public outcry and official investigations. Throughout the 1950s and 60s, sonic boom complaints multiplied. Fighter jets operating near populated areas would inevitably produce booms heard on the ground. Initially, these were seen as the acceptable price of military readiness, but the complaints kept mounting. Between 1956 and 1968, the United States Air Force received more than 38,000 sonic boom damage claims. Of these, approximately 14,000 were approved for payment. The damages ranged from broken windows and cracked plaster to assertions that livestock had been driven insane or pets had died from the shock. While some claims were undoubtedly exaggerated or fraudulent, many were legitimate. Sonic booms were causing real damage and real distress. One particularly infamous incident occurred in 1964 in Oklahoma City. NASA and the Federal Aviation Administration launched what they called the Oklahoma City Sonic Boom Tests. For 6 months, the residents of Oklahoma City were subjected to 8 sonic booms per day as supersonic aircraft flew overhead. The stated goal was to gather data about how people would react to routine sonic booms, information deemed crucial for the planned development of a supersonic transport that would fly regularly over populated areas. Researchers carefully measured the boom characteristics and structural responses. They conducted surveys and interviews to assess public tolerance. The results were devastating for the supersonic transport program. During those 6 months, the FAA received 4,629 damage claims and 15,116 formal complaints. The scientific data showed that sonic boom overpressures varied wildly, sometimes reaching values 200% higher than predicted. More importantly, the public response made one thing crystal clear: people would not tolerate routine sonic booms. The psychological impact of repeated, unpredictable explosions overhead proved far more significant than purely acoustic measurements suggested. In 1969, the government lost a class action lawsuit related to the Oklahoma City tests. The writing was on the wall. Supersonic transports would not be welcome over populated land. The physics of sonic booms are simultaneously simple and complex. When an aircraft flies subsonically, it essentially pushes air out of its way. Pressure waves radiate ahead of the aircraft at the speed of sound, giving the air time to move aside smoothly. But when an aircraft exceeds the speed of sound, it outruns these pressure waves. Air molecules don't have time to get out of the way, so they pile up, creating a shock wave. A shock wave is essentially a nearly instantaneous jump in pressure, temperature, and density. The aircraft creates multiple shock waves from various points on its airframe. The nose creates a bow shock. The tail creates another shock. Wings, canopy, and engine inlets all contribute their own shock waves. As these shock waves propagate away from the aircraft and through the atmosphere, something interesting happens. The waves travel at different speeds because the shock waves closer to the aircraft are moving through disturbed air that's already been compressed and heated by previous shocks. The faster moving waves catch up with slower ones and the shocks coalesce. By the time the pressure waves reach the ground, they've typically merged into a distinctive N-wave pattern. Someone on the ground experiences a sudden pressure increase as the bow shock arrives, followed by a period of elevated pressure, then a sudden pressure decrease back below ambient as the tail shock passes. This N-wave is what creates the characteristic double boom, bang bang, that people hear. The strength of the boom depends on several factors. Larger, heavier aircraft create stronger booms because they displace more air. Flying faster makes the shocks sharper and stronger. Flying lower means the shock waves have less distance to spread out and weaken before reaching the ground. A typical supersonic fighter at altitude might produce peak overpressures around 1 to 2 pounds per square foot. That might not sound like much, but it's equivalent to a pressure change that can rattle buildings and shatter windows. The Concorde, when it flew supersonically over the ocean, produced peak overpressures around 1.9 pounds per square foot. The brief tests of military bombers flying supersonically at low altitude had produced overpressures as high as 120 pounds per square foot, enough to cause significant structural damage. During the 1960s and early 70s, the United States pursued an ambitious supersonic transport program, often called the SST. The vision was a fleet of civilian airliners that could cross the Atlantic in less than 3 hours, revolutionizing long-distance travel. Boeing won the design competition with a swing-wing concept that would have been larger and faster than the Concorde. But the SST program faced mounting opposition. Environmental groups raised concerns about emissions and potential damage to the ozone layer. Economists questioned whether the aircraft would ever be commercially viable, and the sonic boom problem loomed over everything. Researchers at NASA's Langley Research Center had been studying sonic booms intensively. One of the key figures was Dominic Maglieri, a brilliant engineer who dedicated his career to understanding every aspect of sonic boom physics. Along with colleagues like Harry Carlson and Wallace Hayes, Maglieri helped develop increasingly sophisticated models of how shock waves formed and propagated. They conducted wind tunnel tests, analysed data from actual supersonic flights, and gradually built a comprehensive understanding of boom characteristics. A crucial theoretical breakthrough came from researchers A.R. Seabass and A.R. George. In 1971, they published work showing that sonic booms didn't have to follow the standard N-wave pattern. By carefully controlling the distribution of volume and lift along an aircraft's length, it might be possible to shape the near-field pressure signature in ways that would result in a very different signature at the ground. Instead of a sharp N-wave with instantaneous pressure jumps, you could potentially create a flat-top signature where pressure rose gradually, stayed elevated for a period, then decreased gradually. Or you could create a ramp signature where pressure increased steadily throughout the boom. Christine Darden, working at NASA Langley, made further crucial contributions. She modified the Seabass-George theory to account for realistic atmospheric conditions rather than the simplified isothermal atmosphere the original theory assumed. She developed computer codes that could predict how shaped signatures would propagate through the standard atmosphere. Her work showed that shaped booms could persist through the atmosphere without degenerating into N waves, but only if the shaping was done correctly and the aircraft flew at appropriate altitudes. These theoretical advances were exciting, but they remained just that: theoretical. No one had actually built and flown an aircraft specifically designed to produce shaped sonic booms. The mathematical models made predictions, but models can be wrong. The atmosphere is turbulent and variable. Small imperfections in aircraft shape could destroy a carefully crafted signature. Questions remained about whether shaped booms would actually persist from cruise altitude all the way to the ground, or whether they would inevitably sharpen back into N waves during propagation. The cancellation of the American SST program in 1971 marked a turning point. With no near-term prospect of supersonic airliners, funding for sonic boom research dried up. The Concorde entered service in 1976, but it was confined to routes over water. British Airways and Air France operated profitable transatlantic services, but the Concorde would never fulfill its designer's dreams of flying across continents. Without the ability to fly supersonically over land, the economics of supersonic transport became marginal at best. The Concorde remained a technological marvel and a status symbol, but it couldn't spark the revolution in air travel its creators had envisioned. For more than 2 decades, sonic boom research languished. NASA continued some basic studies, but without a driving application, progress slowed. Engineers and scientists who had devoted their careers to understanding sonic booms retired or moved to other fields. The conventional wisdom hardened. Sonic booms were simply too loud, too startling, too damaging to ever allow routine supersonic flight over populated areas. If you wanted to fly faster than sound, you had to do it over the ocean or remote desert areas where the booms wouldn't bother anyone. But by the late 1990s, interest began to revive. Advances in computational fluid dynamics made it possible to model shockwave formation and propagation with unprecedented accuracy. New aerospace companies were expressing interest in small supersonic business jets that could carry executives across continents in a fraction of the time required by subsonic aircraft. Military planners were thinking about long-range supersonic reconnaissance and strike aircraft. And the Defense Advanced Research Projects Agency, DARPA, decided it was time to revisit the sonic boom problem with fresh eyes and modern technology. The answer to whether shaped sonic booms would actually work in practice was about to be found. But first, researchers needed to find the right aircraft to modify. the right team to design the modifications, and the right test program to gather definitive data. All of those elements would come together around an aircraft that, at first glance, might have seemed an unlikely choice. A small, lightweight fighter designed in the 1950s, a plane that had proven itself in combat, training, and reconnaissance roles around the world. The story of how the F-5 Tiger became the sonic boom demonstrator is a fascinating tale in itself. The Tiger's tale, how a lightweight fighter became a sonic boom laboratory. In 1954, the United States Air Force and Navy were deep in the throes of the Cold War, pursuing supersonic combat aircraft of ever-increasing size, complexity, and cost. The F-100 Super Sabre, F-101 Voodoo, F-102 Delta Dagger, and F-104 Starfighter were either entering service or in advanced development. These were specialized, high-performance machines designed for American air crews and American missions. But a prescient government study warned that many of America's allies needed something different. These nations couldn't afford massive, complicated fighters. They needed smaller, simpler aircraft that would still deliver supersonic performance, but do so economically. Thomas Jones and his colleagues at Northrop Corporation immediately recognized an opportunity. Jones, a chief engineer who would eventually succeed founder Jack Northrop as company president in 1959, believed there was a substantial export market for a fighter that was not just affordable to purchase, but also cost-effective throughout its entire service life. This philosophy drove the design from the beginning. Northrop's team prioritized maintainability. The aircraft would have numerous access doors and removable panels, making it easy for ground crews to reach components. Systems would be designed with interchangeable, easily replaced parts. The goal was an aircraft that could be operated and maintained with minimal support infrastructure, perfect for nations with less developed military logistics systems. The design team came up with a concept they designated the N-102. The breakthrough came with General Electric's development of the J-85 turbojet, a small but surprisingly powerful engine. By 1955, the design had evolved into the N-156, a lightweight aircraft that Northrop hoped might interest the United States Navy for operations from small escort carriers. That particular hope faded when the Navy announced it was retiring those ships. However, the Air Force had released a requirement for a supersonic trainer, and Northrop saw another opportunity. Applying the area rule, a technique developed by Richard Whitcomb at NACA that involved shaping the fuselage to minimize transonic drag, Northrop created the T-38 variant, designated TZ-156 during development. The prototype, designated YT-38, began flight tests at Edwards Air Force Base in April 1959. The results exceeded expectations. The T-38 was fast, reaching speeds up to 820 miles per hour with ease. It was agile and responsive. It was reliable. The Air Force placed an initial order for 50 aircraft in October 1959, the start of a production run that would eventually reach almost 1,200 aircraft and continue until 1972. The T-38 Talon, as it was named, became an iconic aircraft. Generations of Air Force pilots received their advanced training in T-38s. NASA used them for astronaut training and proficiency flying. Decades later, at the time of the shaped sonic boom demonstration, T-38s were still in frontline service for pilot training. The aircraft's longevity testified to the fundamental soundness of its design. But while Northrop was developing the T-38 trainer, the company was also pursuing the original fighter version. The N-156F lightweight fighter prototype was built using corporate funds in early 1958. The Air Force agreed to purchase 2 more prototypes, and the first made its maiden flight at Edwards on July 30, 1959. The aircraft went supersonic during this first flight, remarkably without the engine even having an afterburner installed. Encouraged by these excellent test results, Northrop spent the next several years weaponizing the design. Internal guns, bomb racks, missile pylons, external fuel tanks, and reinforced structures transformed the basic airframe into a capable combat aircraft. The result was designated F-5A Freedom Fighter for single-seat versions and F-5B for two-seaters. After the Air Force awarded production contracts in October 1962, Northrop built F-5As and F-5Bs alongside T-38S on its highly efficient assembly line in Hawthorne, California. The F-5B entered operational service as a trainer in April 1964, followed 4 months later by the F-5A. Given the aircraft's intended international role during the Cold War, the Air Force chose an appropriately symbolic name, Freedom Fighter. The F-5 received its combat baptism in Vietnam. In October 1965, the Air Force deployed 12 modified F-5As to South Vietnam for a 6-month combat evaluation codenamed Scotia Tiger, meaning Little Tiger. These aircraft had been modified with aerial refueling capability and additional armor to protect against small arms fire. During the evaluation, the F-5As flew 2,664 sorties. While they didn't fly enough missions over North Vietnam to truly test air-to-air capabilities, they performed well in ground attack roles. Their maintenance requirements compared favorably with the larger, more complex F-4 Phantom II and even the older F-100 Super Sabre. After Scotia Tiger concluded, the F-5As formed the nucleus of a US unit in Vietnam before being transferred to South Vietnamese forces in 1967. Meanwhile, other nations were beginning to receive F-5S through US military assistance programs. By 1972, 15 nations had acquired F-5As, F-5Bs, and reconnaissance variants through US assistance or foreign military sales. Additional aircraft were being built under license in Canada and Spain. The F-5 Freedom Fighter proved its value, but Northrop believed they could do better. Based on feedback from Vietnam operations and input from foreign operators, the company developed an improved version, originally called the F-521. This upgraded fighter would be better able to engage late-model Soviet MiG-21 fighters. Rather than simply accepting Northrop's unsolicited proposal, the Air Force decided to hold a competition, calling it the International Fighter Aircraft Program. Lockheed, McDonnell Douglas, and Lingtemco Vought submitted modified versions of existing fighters to compete against the upgraded F-5. In November 1970, the Air Force declared Northrop the winner, with an initial contract for 340 aircraft. 1 month later, the aircraft received official designations F-5E for single-seaters and F-5F for the two-seat version. The Air Force initially tried to call it the International Fighter Aircraft, but the name never stuck. Eventually it was renamed Tiger II, partly in memory of Scotia Tiger. The F-5E made its maiden flight in August 1972, followed by the F-5F in September 1974. The F-5E represented a substantial improvement over the original F-5A. General Electric's more powerful J8521 engines provided 20% more thrust. The wing area increased by 9%. New leading-edge extensions ran all the way to the wing roots, improving maneuverability. The fuselage grew larger to accommodate more internal fuel. A sophisticated fire control system included an Emerson AN/APQ 153 radar, computing gun sight, missile launch computer, air data inputs, and a gyroscopic platform. With a maximum takeoff weight of 25,350 pounds, a combat ceiling above 50,000 feet, and a ferry range exceeding 1,550 miles, the F-5E was a formidable lightweight fighter. Its maximum speed of Mach 1.64 at 36,000 feet made it genuinely supersonic in level flight. Northrop's Hawthorne facility eventually built 792 F-5Es and 140 F-5Fs, plus 12 RF-5E reconnaissance variants called Tiger Eyes. Licensed production in Switzerland, South Korea, and Taiwan added more than 500 additional aircraft. But perhaps the most interesting application of the F-5E in American service had nothing to do with combat. Instead, it became the ultimate training tool for fighter pilots. The heavy losses suffered by large US fighter bombers during the Vietnam War had sparked a revolution in fighter pilot training. North Vietnamese MiG-17 and MiG-21 interceptors, using hit-and-run tactics, had proven devastatingly effective against larger American aircraft. In 1969, the Navy established the Fighter Weapons School at Naval Air Station Miramar near San Diego, California. This school, made famous by the nickname Top Gun, emphasized realistic combat training. A key innovation was dissimilar air combat tactics, or DACT. American pilots would train against small, agile aircraft like the Douglas A-4 Skyhawk that simulated the characteristics of Soviet fighters. The Air Force followed suit, forming its own adversary training squadron in 1972. The ideal aircraft would be the F-5E, whose size, performance, and smokeless engines closely matched the MiG-21. Unfortunately, the Air Force didn't own any F-5Es when the 64th Aggressor Squadron formed at Nellis Air Force Base, Nevada. Instead, the squadron flew Northrop T-38S, which proved effective but began suffering premature wear from the strenuous maneuvers. Fate intervened in May 1975 with the sudden fall of Saigon. 70 brand new F-5Es that had been earmarked for South Vietnam became available. These aircraft equipped not only the 64th Squadron, but also 2 additional aggressor squadrons in Nevada, England, and later the Philippines. Painted in a variety of exotic camouflage schemes to simulate Soviet aircraft, these F-5Es helped hone the skills of US Air Force fighter pilots throughout the rest of the Cold War. Those skills were dramatically demonstrated during Desert Storm air operations in early 1991. The Navy and Marines also extensively used F-5Es for aggressor training. When the Navy moved its Top Gun program from Miramar to Naval Air Station Fallon in northwestern Nevada in 1996, Composite Fighter Squadron 13, VFC-13, converted from FA-18 Hornets to F-5E Tiger IIs to provide adversary training. The Marine Corps operated a similar unit, Marine Fighter Training Squadron 401 VMFT 401 at Marine Corps Air Station Yuma, Arizona. By the late 1990s, these aggressor F-5Es had accumulated tens of thousands of flight hours in demanding roles. The aircraft had been thrown into aggressive maneuvers, pulled to high G-forces, and generally worked hard. They were showing their age. To extend their service life, the Navy contracted with Northrop Grumman in 1999 to perform depot-level maintenance at the company's St. Augustine, Florida facility. Northrop Grumman and its subcontractors also continued providing spare parts, modifications, and technical support for the hundreds of F-5s still flying with foreign air forces, many now serving as advanced trainers rather than frontline fighters. All of these factors made the F-5E an excellent choice for the shaped sonic boom demonstration. The aircraft's supersonic capability was proven. Its lightweight, high fineness ratio, blended canopy, and relatively long forebody with aft-mounted engine inlets all contributed to favourable sonic boom characteristics. Northrop Grumman had extensive experience creating longer-nosed variants, specifically the two-seat F-5F and the RF-5E reconnaissance version, with noses up to 42.5 inches longer than the standard F-5E. Crucially, the company had collected extensive analytical and flight test data while developing these variants. From a practical standpoint, operating costs for F-5S were relatively low compared to larger, more complex fighters. Parts were available, maintenance procedures were well established, and Northrop Grumman had people who knew the aircraft intimately. Joseph Polowski, who would become the program manager for the SSBD project, had spent the first 10 years of his career working on F-5E and RF-5E programs. He knew the aircraft's systems, structures, and characteristics better than almost anyone. There was just one catch. Northrop Grumman didn't actually own any F-5Es to modify. The company that had designed and built the aircraft no longer had any in its inventory. Finding an appropriate aircraft and securing permission to modify it would become one of the project's first major challenges. But before we explore how the team solved that problem, we need to understand how the shaped sonic boom demonstration project came to exist in the first place, and the broader program context in which it operated. The birth of the Quiet Supersonic Platform Program. As the 1990s drew to a close, the aerospace community was experiencing a renewed wave of interest in supersonic flight. The Concorde was still flying transatlantic routes, proving that supersonic transport could work technically even if the economics remained challenging. Several companies were exploring concepts for smaller supersonic business jets. Advances in computational fluid dynamics had reached a point where engineers could model complex shockwave interactions with unprecedented accuracy. Material science had progressed, offering new options for lightweight, heat-resistant structures. And perhaps most importantly, there was a growing belief that with modern technology, the sonic boom problem might finally be solvable. This convergence of technological capability and market interest caught the attention of DARPA, the Defense Advanced Research Projects Agency. DARPA's mission has always been to push the boundaries of what's possible to fund high-risk, high-reward research that might be too speculative for conventional programs. In the year 2000, DARPA initiated a new program examining the impact of advanced technology and innovative design approaches on supersonic cruise aircraft. They called it the Quiet Supersonic Platform Program, or QSP. The driving premise of QSP was that advanced technology and innovative configurations could dramatically reduce both the size and environmental impact of supersonic cruise aircraft, whether military or civilian. Initially, DARPA identified 3 potential military roles for quiet, efficient supersonic aircraft: reconnaissance vehicles, medium bombers, and high-speed transports capable of quickly delivering critical equipment to forward operating locations. This last application most closely resembled the mission profile of a supersonic business jet. The program goals were ambitious. DARPA wanted to achieve supersonic flight over land without adverse sonic boom consequences, defining acceptable as boom overpressure rise less than 0.3 pounds per square foot. For context, a conventional supersonic fighter might produce 1 to 2 pounds per square foot, and the Concorde produced about 1.9. 0.3 represented a dramatic reduction. The program also aimed for increased unrefueled range approaching 6,000 nautical miles, gross takeoff weight approaching 100,000 pounds, increased area coverage, and lower overall operational costs compared to existing supersonic aircraft. The vision was to motivate approaches to sonic boom reduction that bypassed incremental improvements and instead pursued breakthrough technologies. DARPA wanted to validate multiple innovative concepts that could ultimately be integrated into efficient, quiet supersonic vehicles. The core technical challenge centered on noise reduction, not just sonic booms, but also takeoff and landing noise. In Phase 1 of QSP, there was only one hard requirement: a sonic boom signature with an initial overpressure of not more than 0.3 pounds per square foot. Other goals supported reaching this requirement. DARPA structured QSP around 3 systems integrator teams: Northrop Grumman, Boeing, and Lockheed Martin. Each team would explore different approaches and technologies. In addition, propulsion companies and smaller organizations would develop specific critical technologies. The program would also foster collaboration among government research centers, particularly NASA facilities that had decades of experience with sonic boom research. Dr. Richard Walesian served as DARPA's QSP program manager. Walesian had previously worked at NASA Langley Research Center and understood the history of sonic boom research intimately. He recognized that while theory suggested shaped sonic booms might work, the theory had never been validated with an actual aircraft flying under real atmospheric conditions. Proving that shaped booms would persist from cruise altitude to the ground represented a critical milestone. Without that proof, any investment in designing quiet supersonic aircraft would be based on unvalidated assumptions. At Northrop Grumman's Integrated Systems sector, Charles Boccadoro led the QSP effort. Boccadoro assembled a talented team that included veterans of the company's various advanced aircraft programs. In June 2001, he selected Joseph W. Pawlowski as the manager for Northrop Grumman's sonic boom demonstration proposal. Pawlowski brought extensive systems engineering experience. Since being hired by Northrop in 1973, he had worked on a remarkably diverse array of aircraft and systems. His decade of direct experience with the F-5 family would prove invaluable. Working alongside Pawlowski was David H. Graham, an aerodynamicist from Northrop Grumman's Advanced Air Vehicle Design Office. Graham had specialized expertise in wave drag, having worked on the company's stealthy YF-23 Advanced Tactical Fighter prototype. His understanding of how shockwaves formed and interacted would be crucial for designing modifications that would produce the desired shaped boom. To bolster their internal expertise, Northrop Grumman engaged outside specialists. Eagle Aeronautics, a small company in Hampton, Virginia, became a key partner. Eagle's founder, Dominic Maglieri, had spent decades as one of NASA's premier sonic boom researchers. After retiring from NASA, Maglieri had continued pursuing his passion through Eagle Aeronautics. He had long advocated for practical flight demonstrations to validate theoretical work. His colleague Percy Bobbitt, known as Bud, brought additional analytical expertise. Weil Laboratories, based in Arlington, Virginia, contributed critical sonic boom prediction capabilities. Ken Plotkin and Juliet Page at Weil had developed sophisticated computer codes for modeling how sonic booms propagated through realistic atmospheres. Their PC Boom software could take near-field pressure signatures from aircraft and predict what the boom would sound like on the ground, accounting for atmospheric effects, temperature gradients, winds, and turbulence. In the late summer of 2000, Pawlowski and Graham went on fact-finding trips to gather information on sonic boom mitigation approaches. In Hampton, Virginia, they visited Eagle Aeronautics, where Maglieri described his ideas for a low-cost sonic boom demonstrator. Later, at Georgia Institute of Technology in Atlanta, they met with Ken Plotkin, who was there on a visit from his Arlington office. Plotkin shared his thoughts on sonic boom minimization. The conversation continued when Plotkin gave Pawlowski a ride to the airport afterward. These discussions helped shape Northrop Grumman's thinking about how best to approach the demonstration challenge. Although DARPA had not originally planned for a sonic boom demonstration as an initial part of the QSP program, Boccadoro's team became interested almost immediately in Maglieri's long-standing proposal to use a modified Ryan BQM 34E Firebee remotely piloted vehicle. The Firebee's modular construction, performance characteristics, and interchangeable components made it attractive in theory. Previous wind tunnel data existed, and perhaps not coincidentally, Northrop Grumman had recently acquired Teledyne Ryan, the company that had built the Firebees. In anticipation of a future sonic boom demonstration contract, Northrop Grumman acquired all the Navy's usable BQM-34E components except engines that were still being used in subsonic Firebee variants. Airframes and spare parts were trucked from Naval Air Weapons Station Point Mugu, California, to Northrop Grumman facilities along Aviation Boulevard in El Segundo. But by early 2001, the Firebee option was running into problems. NASA analysis indicated the Firebee airframe might not be long enough to demonstrate a definitive shaped boom signature. Computational fluid dynamics modeling raised concerns about shock waves from the jet engine inlet located under the airframe. And when technicians inspected the Firebee components that had been stored outdoors in the corrosive salt air at Point Mugu, they found significant deterioration. The Firebee idea went onto the back burner. David Graham suggested an alternative. Northrop Grumman's F-5 family included multiple variants with different nose lengths. The two-seat F-5F trainer and the RF-5E reconnaissance version had noses up to 42.5 inches longer and of different shapes than the basic F-5E. Perhaps flying each variant supersonically at short intervals over pressure sensor arrays could demonstrate differences in sonic boom signatures, all at minimal cost. It was an ingenious low-budget approach. Preliminary analysis in February 2001 by Graham and his colleague Hideo Ikawa, followed by more detailed sonic boom modeling by Eagle Aeronautics, revealed the flaw in this plan. All the signatures would still be typical N waves. The longer noses didn't have the smooth equivalent area distribution needed to produce flat-top or ramp-type signatures. Dominic Maglieri had actually predicted this outcome 2 months earlier. He determined that while the longer noses were beneficial, they weren't shaped correctly for boom minimization. But Maglieri saw potential. The F-5, he thought, would be an excellent candidate for a new, properly designed nose extension that could reshape the initial pressure rise into a flat-top signature. It would be similar to what had been proposed for the Firebee, but using a much more suitable platform. Of all the supersonic fighters in the US inventory, the F-5E was uniquely suitable for such modification. On March 12, 2001, key members of Northrop Grumman's QSP team, including Maglieri and Bobbitt, briefed Richard Lezian at DARPA on 3 options for demonstrating shaped sonic boom persistence. The options were, first flying 2 F/A-18S in close over and under formation to generate a flat-top signature, following up on a test NASA Dryden had performed in 1994. Second, testing Eagle Aeronautics' long-standing Firebee proposal with modified and unmodified aircraft. And third, comparing signatures from a baseline and specially modified F-5E. Except for cost considerations, the third option was clearly the best choice technically. In April 2001, DARPA formally solicited proposals from all 3 systems integrators on how best to demonstrate shaped sonic boom persistence. DARPA added an interesting twist to this mini-competition. The winner would not only need to propose the best technical and cost plan, but also the best plan for incorporating design reviews by the other systems integrators and for sharing data among all QSP participants. This collaborative requirement aligned with DARPA's philosophy that breakthroughs often emerge from open exchange of ideas rather than proprietary secrecy. Northrop Grumman responded that same month with a proposal structured as a cooperative effort involving multiple companies and government agencies. The company submitted its preliminary design for modifying an F-5E with a specially shaped nose extension. The proposal's cover featured a CFD-generated image showing the modified aircraft's hoped-for shockwave pattern, visually communicating the concept. DARPA evaluated all three proposals and, in late July 2001, awarded a $3.4 million contract to Northrop Grumman's Integrated Systems sector. The contract, number MDA 972-0120-017, authorized the company to begin preparing its flight demonstration of shaped sonic boom signatures using F-5Es. NASA Dryden Flight Research Center would be responsible for data collection, given its sonic boom experience, resources, and credibility. Northrop Grumman officially came under contract in mid-August when the first payment arrived. Several weeks before the formal contract award, DARPA had invited key stakeholders to a shaped sonic boom workshop on July 10, 2001, in Valencia, California, just north of Santa Clarita. Attendees came from Northrop Grumman, the other two systems integrators, NASA centers, the Air Force, and various contractors and universities. Consistent with DARPA's rule that anyone participating in the demonstration would share in the data, the workshop examined how various organizations could contribute to the project. Among the participants who would become core members of the Sonic Boom Demonstration Working Group were Peter Cohen from NASA Langley, Edward Herring from NASA Dryden, Mark Gustafson from the Air Force Research Laboratory representing DARPA as its technical agent, and John Morgenstern, Lockheed Martin's veteran sonic boom specialist. The working group also included Plotkin and Page from Weil and Maglieri, and Bobbitt from Eagle. After the contract award, Joe Pawlowski began formally establishing what would be called the Shaped Sonic Boom Demonstration Working Group, or SSBDWG, because members were scattered across the United States. Getting everyone together physically would be difficult. Pawlowski set up a special website for sharing information and ideas. Later, this information was also posted on DARPA's website for access by government participants. As weeks passed, additional experts from NASA Langley, NASA Dryden, Boeing, Lockheed Martin, Gulfstream, and Raytheon joined the working group. Eventually, more than 30 people served as members. 9 of these formed the SSBD program management team: Richard Lesion and later Stephen Walker from DARPA, Charles Boccadoro and Joe Pawlowski from Northrop Grumman, Mark Gustafson from the Air Force Research Laboratory, Peter Cohen from NASA Langley, and Ed Herring, David Richwain from NASA Dryden, along with Roy Martin, Northrop's chief test pilot. Initially, Northrop Grumman optimistically predicted conducting the flight tests at Edwards Air Force Base in summer 2002, requiring about 18 sorties. But many challenges lay ahead. Before DARPA would authorize obtaining an aircraft to modify, the company had to complete an approved design. And before that design could be finalized, the team needed to better understand shock waves generated around jet engine inlets, measuring shock waves. The inlet spillage tests. One of the first priorities of the newly formed Shaped Sonic Boom Demonstration Working Group was planning an in-flight shockwave measurement campaign. NASA's Ed Herring had valuable experience from sonic boom flight experiments Dryden had conducted in the 1990s. During those tests, aircraft had probed shockwaves from other supersonic aircraft in flight, using specially instrumented nose booms to measure pressure variations with exquisite precision. Herring understood that inlet shockwaves could be problematic. When a jet engine inlet captures air at supersonic speeds, some of the air spills around the inlet rather than entering it. This spillage creates additional shock waves that could interfere with the carefully shaped boom signature. Herring proposed conducting preliminary F-5E flight tests to accurately measure shock waves and expansion regions coming off various parts of the aircraft, with particular attention to inlet spillage shocks. He suggested using one of Dryden's F-15S or F/A-18Ss as a probe aircraft, flying in close formation with an F-5E to measure the pressure field. This test could happen as early as December 2001 if arrangements moved quickly. The first prerequisite was arranging for Naval Air Station Fallon to deploy one of VFC-13's F-5Es to Edwards. Roy Martin, Northrop Grumman's chief test pilot, went to Fallon in mid-August 2001 to begin negotiations. Martin was uniquely qualified for this role. A veteran of more than 200 F-4 combat missions over Vietnam, a distinguished graduate of the Air Force Test Pilot School, and holder of a master's degree in aeronautics and astronautics from Stanford, Martin had flown dozens of aircraft types and logged 6,000 hours in the T-38 and F-5 family. He had also flown high-stress flight tests of the F-5 for the Navy in 2000. His extensive contacts throughout the civilian and military test pilot community would prove invaluable. At Fallon, Martin discussed the project with VFC-13's operations officers and pilots. He also had a fortunate encounter with Mike Ingalls, a manager at Northrop Grumman's St. Augustine facility that performed F-5 depot maintenance. Ingalls informed Martin that the Navy was reviving a proposal to purchase surplus Swiss F-5Es with relatively low flight hours to replace its heavily used aggressor aircraft. Once that deal went through, obtaining a Navy F-5E for modification wouldn't be difficult. The first meeting of the Shaped Sonic Boom Demonstration Working Group occurred at Northrop Grumman's Advanced Systems Development Center in El Segundo on August 22, 2001. Those who couldn't attend in person participated via the new website and special telephone connections. Initially, the group planned to meet for approximately 2 hours every other Thursday, though scheduling conflicts would make the actual cadence somewhat irregular. Pawlowski described the working group's approach. Meetings were designed to encourage team interaction and brainstorming. The goal was reaching technical consensus among members in formulating and executing the program. Meetings would also support critical decision points at scheduled milestone reviews. This collaborative philosophy aligned with DARPA's intent that the demonstration benefit the entire supersonic research community rather than just one contractor. By February 2002, some members were brainstorming a new name for both the working group and the overall project, which was occasionally being referred to in jest as silent but deadly. Creative suggestions included boom shaping technology, or BOOST, and the Boom Aerodynamic and Atmospheric Attenuation Demonstration, or BAAD. The final choice was less colourful but descriptive: the Shaped Sonic Boom Demonstration, SSBD. The working group abbreviation became SSBDWG. Meanwhile, planning for the inlet spillage shock measurements accelerated. Herring, the Dryden test pilot Dana Purifoy, and others worked out flight profiles and sensor locations. One major issue involved the attributes of the Navy's F-5E aggressor configuration. The aircraft had permanently installed wingtip missile launch rails and normally carried a tactical air combat training system telemetry pod. These protrusions could affect shockwave formation and needed to be accounted for in the analysis. Another seemingly simple requirement illustrated the complexity of test planning: installing GPS equipment in the F-5E cockpit. As Herring explained, measuring sonic boom signatures involved two components: the measured pressure and the relative position of the aircraft. A discrepancy of several inches could make a significant difference when measuring shockwave behavior. Edwards Air Force Base's sophisticated radars couldn't be depended on to track aircraft locations to within 20 feet. During F-16 XL SR-71 tests in the 90s, radar anomalies had sometimes resulted in position errors of 1,000 feet. Martin and Herring spent much of their time over the next month researching and testing GPS units that would be accurate enough yet small enough to fit in the F-5E cockpit without interfering with ejection sequences, a critical safety concern. They eventually determined that an Ashtec Z12 GPS unit with UHF modem and power supply would fit in the right-hand console with some modifications, including removing a duplicate radio and using a slightly larger map case that Northrop Grumman technicians would fabricate. When Martin presented this proposal to VFC-13, officers in the squadron's chain of command recommended a top-down approval process. The proposal was elevated to Naval Air Systems Command, NAVAIR, at Naval Air Station Patuxent River, Maryland, where specialists conducted a thorough review. Northrop Grumman's Electrical and Data Systems Design Office responded to NAVAIR's concerns with detailed layouts showing the GPS and modem setup, including all wiring. This data package was delivered to NAVAIR on December 21, 2001. While awaiting Navy approval, Herring planned the routes and profiles the F-5E and F-15B would follow during in-flight measurements, as well as the location of ground sensors. He worked closely with David Richwine, Dryden's F-15B manager, and Tim Mose, the F-15B chief engineer. Dave Graham noted Herring's central role. If in doubt, use ED's values. This is his test. We are all just very interested observers. A Fallon flight safety specialist found the basic flight plan acceptable. VFC-13's operations officer assured Martin of pilot qualifications. All were second-tour fleet fighter pilots highly experienced in formation flying and multiplane operations. Early in January 2002, scheduling conflicts involving Dryden's F-15B pilots pushed the test to mid-February, which actually provided more time for Navy approval. On January 23rd, having done a fit test with an F-5E at Fallon, Martin delivered the GPS and associated equipment from Dryden to El Segundo for installation in the custom-built map case. After sending an apparent approval on January 30th, a NAVAIR official apologetically informed Pawlowski that the command still needed to verify electrical connections and effects on instrumentation. With Pawlowski having key Northrop Grumman employees at Patuxent River expedite the process, NAVAIR's final clearance came through on February 8, 2002, just in time. NASA Dryden activated its schedule. Dana Purifoy flew Northrop technicians and Ed Herring to Fallon in one of Dryden's small passenger planes on Monday, February 11th. Purifoy briefed Lieutenant Commander Edgar Higgins, callsign Sting, VFC-13's chosen pilot, on operating procedures at Edwards while the GPS equipment was being installed. Navy technicians checked for electromagnetic interference. Herring used a receiving radio modem to ensure the GPS package transmitted data properly. The team also requested removal of the F-5E's centerline fuel tank, since its shockwaves would be incompatible with the SSBD design. Higgins flew the F-5E down to Edwards the following morning. As he entered the base's airspace, Purifoy met him in an FA-18 to familiarize Higgins with the test area and verify data reception from the F-5E's GPS equipment. After landing for fuel, Higgins's F-5E and Purifoy's accompanying F-15B took off for the first of two flight tests on February 12, 2002, flying at approximately Mach 1.4 in both directions through the Edwards Supersonic corridor. The pair completed two similar test sorties on February 13th, with Higgins returning the F-5E to Fallon later that day. Using its special nose boom with sensitive pressure instrumentation, the F-15B gathered 56 supersonic shockwave signatures from the F-5E at distances ranging from 60 feet to 1,355 feet. Various sensors on the ground collected abundant data in their sonic boom carpets. After the first sorties on February 12th, Herring immediately sent working group members encouraging preliminary data, arriving just in time for a previously scheduled interim design review the next day in El Segundo. He also shared an intriguing atmospheric phenomenon. A NASA employee at one sensor site could see shockwaves in the clouds for one pass. The shocks hit a sundog, a bright spot of light caused by ice crystals, increasing its brightness about 10 times. This lasted 5 to 10 seconds before fading. The observer guessed the shocks might have crystallized water vapor or melted ice crystals. Of course, he didn't have a camera. Northrop Grumman reimbursed VFC-13 for expenses, while Peter Cohen arranged for Dryden to receive special NASA Supersonic research funding to cover its portion. Expressing gratitude for the Navy's support, Pawlowski acknowledged it took a series of small miracles to pull this off. The precedents set in working with the Navy boded well for future F-5E deployments. The entire inlet spillage shock measurement project served as an excellent dry run for the shaped sonic boom demonstration itself. After refinement and validation of the flight test data, including correcting some inexact GPS readings, the working group's engineers and scientists went to work analyzing data and applying it to computational fluid dynamics models. Major participants in this effort included Northrop Grumman's David Graham, Keith Meredith as CFD lead, John Darlin as Deputy Program Manager, and Michael Malone as a CFD specialist, along with Juliet Page and Ken Plotkin from Weil Labs and Ed Herring from NASA Dryden. The team selected 4 pressure signatures for CFD validation based on probes with the smallest and most stable vertical separation distances, ranging from 77 to 105 feet, straightest flight paths and steadiest speeds, ranging from Mach 1.396 to 1.448. They used Northrop Grumman's Generalized Compressible Navier-Stokes Finite Volume Code, GCN-F-5, a structured, implicit, finite volume code derived from NASA Ames Research Center's ARC 3D code. The code was first applied in inviscid mode since viscous effects from the F-5E's surfaces were assumed negligible at the measured distances. Later analyses using both inviscid and viscous modes verified negligible differences. The GCNSFV program included extensive boundary conditions useful for measuring inlet flows. Its grid originally contained 8 million data points in the near field, within 0.5 body lengths of the aircraft, and another 4 million out to the midfield, 3 body lengths. The analysts performed repeated calculations and adjustments of GCNSFV's predictions based on actual inlet spillage shock measurement data. By repeatedly refining results and increasing grid points to 14.2 million, concentrated mostly along angles followed by shock waves under the aircraft, analysts eventually validated CFD solution accuracy out to 3 body lengths. They also developed a process to interpolate CFD solutions onto the actual relative flight paths between the F-5E and F-15B during each probe, accurately simulating pressure measurement signatures. Among lessons learned, they found that determining the 2 aircraft's relative speeds and flight paths, both vertically and horizontally, was critical for accurate correlations. Even knowing the exact location of the F-5E's GPS antenna down to centimeters and the plane's precise angles of attack with decreasing fuel levels was important. Taking all data into account, the CFD code's post-processed pressure signatures compared very well with those collected during in-flight probes. The comparison between final CFD computed pressure signatures and the 4 selected flight test measurements provided excellent correlation. For continuing design work on the modified F-5E, inlet spillage shock measurement results confirmed CFD estimates of F-5E inlet performance were acceptable. Indeed, the entire process of inlet spillage shock measurement flight tests and CFD correlation was successful, providing all necessary procedures and confidence in predictive tools needed for the SSBD program. The team now had validated computer models that could accurately predict shockwave patterns around the F-5E. With this crucial validation in hand, they could confidently design the nose extension that would reshape those shockwaves to produce the desired flat-top sonic boom signature, designing the demonstrator from theory to hardware. With validated computational fluid dynamics tools in hand, the Shaped Sonic Boom Demonstration Working Group could begin the detailed design of the nose extension that would transform an ordinary F-5E into a sonic boom shaping laboratory. The design challenge was subtle and complex. Simply making the nose longer wouldn't produce a shaped boom. The nose had to have precisely the right shape to create the correct equivalent area distribution. The concept of equivalent area lies at the heart of sonic boom theory. When an aircraft flies supersonically, it essentially displaces air. From far away, the aircraft looks like a slender body with a certain volume distribution along its length, plus additional volume contributions from lift forces. This combined volume and lift distribution is the equivalent area. The initial shockwave pattern generated by the aircraft, called the near-field signature, depends directly on how this equivalent area changes along the aircraft's length. The Seabass-George Darden theory, refined over decades of research, showed that to create a flat-top signature at the ground, you needed an equivalent area distribution that started with a very gradual increase, essentially a smooth ramp, rather than the abrupt change at a normal nose. The modified F-5E would need a long, carefully shaped nose extension that smoothly increased the equivalent area over a much greater distance than the stock aircraft's relatively blunt nose. David Graham led the aerodynamic design effort. Working with Keith Meredith and other CFD specialists, Graham used the validated GCNSFV code to model different nose shapes and predict their sonic boom signatures. The process was iterative. They would propose a nose shape, run CFD analysis to compute the near-field pressure signature, use Weil's PC boom code to propagate that signature through the atmosphere to the ground, examine the predicted ground signature, then adjust the nose shape and repeat the process. The constraints were significant. The nose couldn't be so long that it created excessive drag or structural problems. It had to be compatible with the F-5E's existing structure, attaching securely to the forward fuselage. It needed to be light enough that it wouldn't adversely affect the aircraft's weight and balance, and practically speaking, it had to be manufacturable and affordable within the program's budget. Through hundreds of CFD runs and optimization iterations, the team converged on a design. The modified nose would extend the F-5E's length by approximately 4 feet. Its shape was unusual, with a very gradual taper that made the aircraft look somewhat like it had a pelican's beak. The cross-sectional area increased very slowly at first, creating the smooth equivalent area distribution necessary for boom shaping. To verify the design, the team built scale models for wind tunnel testing. An existing Northrop Grumman 0.05 scale high-speed F-5E wind tunnel model was modified to match the chosen shape by working group consensus. This model was tested in NASA Glenn Research Center's 8-foot by 6-foot supersonic wind tunnel. The wind tunnel tests served multiple purposes. They verified the CFD predictions of pressure distributions. They checked that the nose extension didn't create unexpected aerodynamic problems like flow separation. And they provided additional data for validating and refining the computer models. The team also created a low-speed model for testing in Northrop Grumman's 7-foot by 10-foot wind tunnel facility. Low-speed tests checked handling qualities, ensuring the modified aircraft would be safe to fly at subsonic speeds during takeoff, landing, and transit flights. The last thing anyone wanted was an aircraft that flew beautifully at supersonic speeds, but had dangerous handling characteristics during landing. While aerodynamic design progressed, other team members worked on structural design and manufacturing planning. The nose extension would be built primarily from composite materials, lightweight yet strong. It would attach to the existing F-5E fuselage using specially designed fittings that could handle the aerodynamic loads without introducing stress concentrations that might cause structural failure. Engineers had to ensure the attachment points were strong enough for all flight conditions, including high-G maneuvers and potential emergency situations, even though the SSBD flights themselves would be relatively gentle. Installation of instrumentation required careful planning. The modified aircraft would carry extensive sensors to monitor its flight conditions, including angle of attack, side slip angle, acceleration, and precise GPS position. All this data would be recorded and telemetered to ground stations in real time. Engineers had to find places to mount sensors and run wiring without interfering with the aircraft's systems or creating openings that might disturb the airflow over the precisely shaped nose. One significant challenge involved obtaining an actual F-5E to modify. As mentioned earlier, Northrop Grumman didn't own any F-5Es. The company needed to acquire one from the Navy. Roy Martin's earlier conversations at Fallon had revealed that the Navy was purchasing low-time Swiss F-5Es to replace its aging Aggressor aircraft. This created an opportunity. The Navy would have surplus F-5Es that were too worn out for continued Aggressor training, but still airworthy enough for the SSBD project, which required far less demanding flight profiles than adversary training. The process of obtaining a Navy F-5E involved negotiations between Northrop Grumman, DARPA, NAVAIR, and VFC-13. The aircraft would technically remain Navy property, loaned to the SSBD project. This arrangement simplified the paperwork compared to an outright purchase. After months of coordination, the Navy agreed to provide an F-5E that would be ferried to Northrop Grumman's facility in St. Augustine, Florida, for modification. The chosen aircraft had a colourful history. It had spent years at Naval Air Station Fallon flying with VFC-13, being thrown around the sky in aggressive manoeuvres, simulating enemy tactics for fighter pilots honing their skills. The aircraft's Aggressor paint scheme featured exotic camouflage patterns designed to make it look like a potential adversary aircraft. Maintenance records showed it had accumulated substantial flight hours but was still structurally sound. Modification work would take place at St. Augustine, where Northrop Grumman already had facilities for F-5 depot maintenance and where technicians were intimately familiar with the aircraft. The St. Augustine team had been maintaining Navy F-5Es for years. They knew every system, every access panel, every quirk of the aircraft. This expertise would prove invaluable during the modification process. The work plan called for stripping off the F-5E's nose forward of the cockpit, installing the new extended nose, integrating all the necessary instrumentation and wiring, conducting ground tests to verify all systems worked correctly, then performing a series of functional check flights before the aircraft would be ready for supersonic boom testing. The schedule was aggressive but achievable if everything went according to plan. As design and planning work progressed through 2002, the Shaped Sonic Boom Demonstration Working Group held regular meetings to review progress, discuss technical issues, and coordinate among the various organizations involved. These meetings brought together people from Northrop Grumman, NASA Langley, NASA Dryden, the Air Force Research Laboratory, Boeing, Lockheed Martin, Gulfstream, Weil Labs, Eagle Aeronautics, and others. The collaborative atmosphere was remarkable. Despite being business competitors in many areas, these companies shared data and insights freely for the benefit of the project. By fall 2002, Northrop Grumman had completed the detailed design and was ready to begin physical modification of the aircraft. The Navy F-5E arrived at St. Augustine. Technicians carefully removed the original nose section, preserving the forward fuselage structure. The new nose extension, fabricated from composite materials with precise dimensional control, was prepared for installation. Fairings were designed to smoothly blend the new nose into the existing fuselage, ensuring the entire shape maintained the smooth equivalent area distribution the design required. Installing the new nose was a delicate operation. The attachment fittings had to align perfectly. Technicians used precise measurement equipment to verify positions and angles. Wiring for instrumentation had to be routed through the nose extension to sensors at the tip and along the length, with every connection triple-checked. The installation of GPS antennas, pitot-static probes, angle of attack sensors, and other instruments required careful placement to get accurate data without disturbing the airflow. Ground testing began as soon as the physical modification was complete. Electrical systems were powered up and checked. The GPS equipment was tested to ensure it could acquire satellites and provide the sub-meter position accuracy required. All the new instrumentation was calibrated. Structural load tests verified the nose attachment could handle expected aerodynamic forces with adequate safety margins. Meanwhile, detailed flight test planning was underway. Ed Herring at NASA Dryden was designing the sensor layouts for ground-based boom measurements. His team would deploy arrays of microphones and pressure sensors along the flight path, creating a boom carpet that would capture the shaped signature at multiple locations. The spacing between sensors, their calibration, their protection from wind and weather, and the data recording systems all required meticulous planning. Dryden would also provide the F-15B chase plane that would fly in close formation with the modified F-5E to measure near-field pressure signatures, just as it had done during the inlet spillage shock measurements. The F-15B's nose boom would be outfitted with the latest pressure transducers capable of capturing shockwave details. Another innovative data collection method involved using a sailplane. The Air Force Test Pilot School at Edwards agreed to provide a Blahnik L-23 glider equipped with a wingtip-mounted microphone and fuselage-mounted pressure transducer. The sailplane would be positioned at around 10,000 feet altitude, below the F-5E's supersonic flight path, but above most atmospheric turbulence. Recording boom signatures in the air between the aircraft and ground would provide data about how the signature evolved during propagation, critical for validating atmospheric models. By spring 2003, the modified F-5E was ready for initial flights. The first flights would be subsonic, checking basic handling qualities and systems operations. If those went well, the team would gradually expand the flight envelope, eventually reaching supersonic speeds. Only after confirming the aircraft flew safely and all systems worked correctly would the boom measurement flights begin. Roy Martin would serve as the primary pilot for the SSBD aircraft. His decades of experience with F-5S, including recent high-stress Navy test flights, made him the ideal choice. Martin thoroughly understood the aircraft's characteristics and quirks. He had the test pilot skills to precisely fly the profiles required for boom measurements, maintaining constant altitude, heading and speed while supersonic, allowing sensors to capture clean data. On July 24, 2003, Roy Martin climbed into the cockpit of the newly modified F-5 E-shaped sonic boom demonstrator at St. Augustine for its first flight. The pelican-nosed aircraft looked strange sitting on the ramp, but Martin knew its appearance belied its potential significance. If this aircraft could prove that shaped sonic booms worked in practice, it could open the door to a new era of supersonic aviation. The engine started without incident. Martin taxied out, ran through his checklist, and received clearance for takeoff. The F-5E accelerated down the runway and lifted off smoothly, heading for Cecil Field for some initial air work. The handling felt normal. The aircraft responded to controls predictably. After about an hour of flying, checking various speeds and configurations, Martin brought the aircraft in for landing at Cecil Field. The first flight was a success. Several more functional check flights followed over the next few days, gradually exploring more of the flight envelope. Then came the moment to fly the aircraft cross-country to California. Martin would pilot the modified F-5E, while a safety pilot flew a T-38 in formation. This would be the flight that opened this chapter, the journey from Cecil Field to Edwards Air Force Base via intermediate stops. As the two Northrop aircraft took off from Jacksonville on that hot July morning, the real work of the shaped sonic boom demonstration was about to begin. The flight tests proving the theory. By late July 2003, the modified F-5 E-shaped sonic boom demonstrator had arrived at Edwards Air Force Base, ready to begin its historic mission. Edwards, with its vast restricted airspace and supersonic corridors, was one of the few places in the United States where sustained supersonic flight over land was permitted. The base had been the site of Chuck Yeager's sound barrier breaking flight in 1947, and it had hosted decades of supersonic research since then. Now it would host the first ever demonstration that sonic booms could be intentionally shaped and reduced through aircraft design. The team assembled at Edwards included personnel from multiple organizations. Northrop Grumman's flight test team, led by Roy Martin, would operate the SSBD aircraft. NASA Dryden provided extensive support, including the F-15B probe aircraft, ground sensor systems, data analysis capabilities, and test coordination. NASA Langley contributed additional sensors and boom prediction expertise. The Air Force provided the test pilot school sailplane with its crew and unique airborne sensors. Weil Laboratories, Eagle Aeronautics, Boeing, Lockheed Martin, and Gulfstream sent representatives to observe and assist. This truly was a collaborative effort. The test plan called for flying the modified F-5E supersonically through designated corridors while maintaining precise flight conditions. Target parameters included altitude around 32,000 feet, speed around Mach 1.4, and level flight along a straight track. These conditions had been carefully chosen based on CFD predictions to produce the clearest shaped boom signatures at ground level. Ground-based sensors would capture the primary data. NASA Dryden engineers had installed an array of 42 sensors stretched along 2.5 miles under the flight path. These sensors included microphones to record acoustic signatures and pressure transducers to measure the actual pressure profile of the boom. The sensors were precisely positioned using GPS surveying, with their locations known to within inches. Data acquisition systems at each sensor position would record at high sampling rates, capturing the fine details of shock waves and pressure changes. The F-15B chase plane would fly behind and below the F-5E, using its instrumented nose boom to measure near-field pressure signatures. This data would show how shock waves formed around the modified aircraft, providing validation of CFD predictions and showing how the shaped signature began to propagate away from the aircraft. The F-15B pilots and instrumentation engineers at Dryden had extensive experience with this type of probing from earlier projects. The sailplane would occupy a middle altitude between the supersonic F-5E and the ground sensors. Flying at 10,000 feet, above most turbulent mixing but well below the F-5E's altitude, the sailplane would record how the signature evolved during atmospheric propagation. This represented a unique data collection approach that had rarely been attempted before. The sailplane's lack of engine noise made it ideal for acoustic measurements, and its slow flight speed meant it could loiter in position for extended periods. Before any boom measurements could occur, the team needed baseline data. An unmodified Navy F-5E would fly profiles identical to those planned for the demonstrator aircraft, generating standard N-wave booms. These baseline measurements would provide the comparison data needed to prove that the modification actually reduced boom intensity. Without proper baselines, it would be impossible to make credible claims about boom reduction. The first test flights began in early August 2003. Initial sorties were partly for pilot proficiency, ensuring Roy Martin was thoroughly comfortable with the modified aircraft's handling at supersonic speeds. They also served to check out all the data collection systems, verifying that sensors were recording clean data, telemetry links were working, GPS tracking was accurate, and the complex coordination among multiple aircraft and ground stations functioned smoothly. As test flights progressed, the team encountered the usual challenges of flight research. Weather conditions had to be suitable, with relatively calm winds and clear skies. The sailplane had to be in position before the supersonic passes. The F-15B had to achieve proper formation position. Ground crews had to confirm all sensors were operating. Coordinating all these elements required careful planning and real-time flexibility when conditions didn't match predictions. The historic breakthrough came on August 27, 2003. On this date, all elements came together perfectly. Weather conditions were ideal. All aircraft were serviceable. Ground sensors were operational. The F-5 E-shaped sonic boom demonstrator flew supersonic passes over the sensor array with Roy Martin precisely maintaining altitude, heading and speed. The F-15B captured near-field signatures. The sailplane recorded midfield data. Ground sensors registered the boom signatures. As data flowed into the control room, researchers could see immediately that something was different. The ground signatures weren't typical N waves. Instead of the characteristic sharp double boom, the pressure traces showed a flat top shape. Pressure rose gradually, stayed elevated for a period, then decreased gradually, exactly as the Seabass-George Darden theory predicted, exactly as the CFD models had shown. The shaped boom had persisted through more than 30,000 feet of atmosphere to reach the ground largely intact. The implications were profound. For the first time in aviation history, researchers had proven that decades of theoretical work on sonic boom minimization actually worked in practice. An aircraft had been deliberately shaped to reduce its sonic boom, and the reduction had been measured and documented under real flight conditions in the actual atmosphere. This wasn't a laboratory experiment or a computer simulation. This was a real airplane generating real shaped booms that sensors on the ground could measure. Over the following weeks, the team flew additional test sorties, accumulating data across a range of flight conditions. They varied altitude slightly, changed speed, flew different headings to account for wind effects. The unmodified baseline F-5E flew comparison passes. The F-15B conducted numerous probing runs, building a comprehensive database of near-field signatures at various distances from the aircraft. The sailplane recorded dozens of midfield signatures. Ground sensors captured hundreds of boom events. By the time DARPA funding concluded in late 2003, the shaped sonic boom demonstration had achieved its primary objectives. The team had proven shaped booms were achievable. They had measured boom reductions of approximately 1/3 compared to unmodified aircraft, consistent with predictions. They had collected extensive data that would support future supersonic aircraft designs. And perhaps most importantly, they had demonstrated that collaboration among government agencies, NASA centers, military services, and competing aerospace companies could produce breakthrough results. The success attracted NASA's attention. The agency's Vehicle Systems program decided to fund a follow-on effort called the Shaped Sonic Boom Experiment, SSBE. Using the same modified F-5E, NASA conducted additional flights in January 2004. These flights expanded the test matrix, exploring different Mach numbers ranging from 1.35 to 1.4 and altitudes from 32,000 to 34,000 feet. The sailplane flew more missions. Additional ground sensors were deployed. By the end of the SSBE campaign, researchers had accumulated more than 1,300 high-quality sonic boom recordings. Ed Herring, NASA Dryden's principal investigator for sonic boom research, noted that in all these flights, the SSBD aircraft produced shaped modified sonic booms. Interestingly, they observed differences in signature shapes with variations in Mach number and altitude, providing valuable data about how flight conditions affected boom characteristics. The data analysis phase would continue for years. Researchers at NASA Langley, NASA Dryden, Northrop Grumman, and partner organizations pored over the measurements, comparing them with predictions, refining computational models, and extracting lessons that could guide future designs. The F-5 E-shaped sonic boom demonstrator had generated an unprecedented database of shaped boom measurements, a resource that would inform supersonic research for decades to come. Peter Cohen, NASA's Supersonic Vehicle Sector Manager, expressed satisfaction with the extensive dataset collected. Researchers now had the information needed to truly understand the details of sonic boom shaping in realistic flight conditions. This understanding would be crucial for designing the next generation of quiet, supersonic aircraft. The technical papers documenting the shaped sonic boom demonstration results were presented at aerospace conferences and published in journals. The project received recognition throughout the aerospace community. In 2003, NASA's Aeronautics Mission Directorate honored the team with a Technical Excellence Award. The American Institute of Aeronautics and Astronautics would later recognize the historical significance of the work. Looking back at the project from the perspective of years later, several factors contributed to its success. The collaborative model that DARPA mandated, requiring data sharing among all participants, created an environment where the best ideas could flourish regardless of their source. The decision to use an F-5E rather than developing a new aircraft or extensively modifying a Firebee kept costs manageable and reduced risks. The extensive preliminary work, including the inlet spillage shock measurements and CFD validation, ensured the design was sound before committing to expensive hardware. And the expertise assembled in the working group, drawing on decades of experience from multiple organizations, provided the depth of knowledge needed to overcome unexpected challenges. Roy Martin's skill as a test pilot proved essential. Flying supersonic test profiles requires precision. Martin had to maintain exact altitude, heading and speed while the aircraft was generating shock waves and experiencing the subtle aerodynamic effects of supersonic flight. Small deviations could compromise data quality. His thousands of hours in F-5s gave him the intimate familiarity with the aircraft needed to fly these demanding missions successfully. The modified F-5E itself performed beautifully throughout the test program. Despite concerns about how the long nose extension might affect handling, the aircraft proved stable and controllable. The composite nose structure held up under aerodynamic loads. The instrumentation systems worked reliably. The aircraft never experienced significant maintenance problems that would have disrupted the test schedule. After the test program concluded, the F-5 E-shaped sonic boom demonstrator was retired from flying status. It had served its purpose, proving that shaped booms were real and achievable. The aircraft was preserved as a historical artifact, a flying laboratory that had advanced aerospace knowledge and opened new possibilities for supersonic flight. Today, It serves as a reminder of what can be accomplished when brilliant engineers, skilled pilots, and dedicated researchers come together to tackle seemingly impossible challenges. Legacy and the path forward. The shaped sonic boom demonstration accomplished something remarkable. It transformed sonic boom research from a field dominated by theory, computer models, and wind tunnel tests into one backed by actual flight data from a real aircraft flying through real atmospheric conditions. The SSBD proved that the Seabass-George Darden theory wasn't just elegant mathematics, but a practical guide for designing quieter, supersonic aircraft. This validation gave aircraft designers confidence that investing in shaped boom technology would actually produce the predicted results. The measured boom reductions, approximately 1/3 compared to unmodified aircraft, might not sound dramatic but represented significant progress. The modified F-5E produced peak overpressures around 0.6 to 0.8 pounds per square foot compared to roughly 1 pound per square foot for the unmodified aircraft. While still above the 0.3 target DARPA had set for the QSP program, the results showed the right direction. More aggressive shaping applied to clean sheet designs rather than modifications of existing aircraft could potentially reach even lower boom levels. Perhaps more important than the absolute numbers was the fact that the shaped signature persisted from cruise altitude to the ground. Some skeptics had worried that atmospheric turbulence, temperature gradients, wind shear, and other real-world effects might destroy carefully crafted signatures during propagation. The SSBD data showed that while atmospheric effects did influence signatures, properly shaped booms maintained their essential character all the way to the ground. The flat-top shape with its gradual pressure rises and falls remained recognizable in ground measurements, validating the atmospheric propagation models. The extensive database of measurements supported numerous follow-on studies. Researchers analyzed how signature shapes varied with Mach number, altitude, atmospheric conditions, and other parameters. They examined how well different computational models predicted the measured results, identifying strengths and weaknesses in simulation tools. They studied the correlation between measured overpressures and various acoustic metrics used to quantify boom loudness. This work refined understanding of boom perception, showing that shaped signatures with their gradual pressure changes were indeed perceived as less startling and annoying than equivalent strength N waves. NASA incorporated lessons from SSBD into its broader supersonic research programs. The agency continued developing computational tools for boom prediction and aircraft design optimization. Wind tunnel facilities at NASA Glenn and other locations conducted additional tests with shaped body models. Human subject studies explored psychological responses to different boom signatures, helping establish acceptable loudness levels for future regulations. These complementary efforts built on the foundation SSBD had established. The aerospace industry took notice. Companies pursuing supersonic business jet concepts began incorporating boom shaping into their designs from the beginning rather than treating it as an afterthought. Gulfstream Aerospace, which had participated in the SSBD working group, continued its own quiet supersonic research. Ariane Corporation, later Ariane Supersonic, developed concepts for shaped boom business jets. Boom Supersonic emerged with plans for supersonic airliners incorporating boom reduction technology. Lockheed Martin's Skunk Works, drawing on decades of experience including participation in SSBD, began conceptual work that would eventually lead to NASA's X-59 quiet supersonic research aircraft. The X-59, officially designated X-59 QuesST for quiet supersonic technology, represents the next generation of shaped boom demonstrators. While the F-5 ESSBD demonstrated boom shaping through nose modifications to an existing fighter, The X-59 is a clean sheet design where every element has been optimized for boom reduction. The aircraft's extremely long, narrow nose accounts for much of its 99-foot length. Its high aspect ratio wing, T-tail configuration, and top-mounted engine inlet all contribute to minimizing shockwave strength. NASA's goal with the X-59 is ambitious, achieving a perceived noise level below 75 decibels compared to typical sonic booms around 100 decibels or more. Rather than a sharp crack or double boom, the X-59 should produce what NASA describes as a quiet thump, perhaps comparable to distant thunder or a car door closing. If successful, this would represent a quantum leap beyond what SSBD achieved. The X-59 program faces challenges the SSBD didn't encounter. As a unique experimental aircraft rather than a modification of an existing design, the X-59 requires substantially more development, time and cost. Its unconventional configuration introduces complexity. The extremely long nose creates structural challenges and affects pilot visibility, requiring an external vision system since the pilot can't see forward through conventional windows. Ground handling with that long nose requires care, and achieving the aggressive boom reduction targets demands tighter manufacturing tolerances and more sophisticated shaping than the F-5E modification required. As of this writing, the X-59 is in final assembly and testing at Lockheed Martin's Skunk Works facility in Palmdale, California. First flight is anticipated in the near future. Following initial flight tests to verify the aircraft's performance and handling, NASA plans to fly the X-59 over communities across the United States, gathering public response data. Residents in selected areas will be surveyed about their reactions to X-59 overflights, providing the human perception data needed to inform future regulations. The ultimate goal is changing regulations that currently ban supersonic flight over land. If the X-59 demonstrates that sonic booms can be reduced to acceptably quiet levels, and if community surveys show people can tolerate these quieter booms, regulators might establish new rules allowing supersonic overland flight for aircraft that meet boom loudness standards. This could finally open the door to routine supersonic commercial aviation across continents, something that has been technically feasible but regulatorily prohibited since the 1970s. The potential economic impacts of practical supersonic commercial flight are substantial. Business travelers could cross continents or oceans in half the time required by subsonic aircraft. A New York to Tokyo flight that currently takes 14 hours might take 7. Los Angeles to Sydney, currently 15 hours, might take 7 or 8. Time-sensitive cargo could reach destinations much faster. Emergency medical supplies, organs for transplant, critical spare parts, all could be delivered in hours rather than days. The value of time savings for business and critical cargo could justify the higher costs of supersonic flight, creating a viable market. Of course, boom noise isn't the only challenge facing supersonic aviation. High-altitude emissions, particularly oxides of nitrogen, could affect the ozone layer and contribute to climate change. Supersonic aircraft require more fuel per passenger mile than subsonic aircraft, raising questions about environmental sustainability. Engine noise during takeoff and landing must meet strict standards. Manufacturing costs for specialized supersonic aircraft will likely remain high, and the market size for supersonic travel remains uncertain. It's unclear how many travelers or shippers would pay premium prices for speed even if sonic booms weren't an issue. But solving the sonic boom problem removes what has been the single greatest barrier to supersonic overland flight. The work done by the SSBD team, and continued by subsequent programs like the X-59, is making that solution increasingly viable. What once seemed impossible, taming the thunder of sonic booms, now appears achievable with careful engineering and design. The story of the shaped sonic boom demonstration reminds us how long the path from theoretical understanding to practical application can be. The fundamental theory of boom shaping was published in the early 1970s. 30 years passed before the SSBD flew in 2003. Another 2 decades of development have been required to reach the X-59. Progress in aerospace is often measured in decades, requiring sustained commitment and patience. The collaborative model pioneered by DARPA for the QSP program and SSBD project offers lessons beyond supersonic flight. By requiring data sharing and incorporating design reviews from competitor companies, DARPA created an environment where collective expertise could be leveraged. Companies brought their unique strengths: Northrop Grumman's experience with the F-5 and systems integration, Boeing's computational capabilities, Lockheed Martin's sonic boom analysis expertise, NASA's flight test experience and atmospheric modeling, Weil's boom propagation software. None of these organizations could have succeeded alone, but together they accomplished something historic. The individuals who made SSBD possible deserve recognition. Joe Pawlowski's systems engineering skills and project management held the effort together through challenges and setbacks. David Graham's aerodynamic expertise shaped the design. Roy Martin's precision flying generated the data. Ed Herring's sensor arrays and measurement techniques captured that data. Dominic Maglieri's decades of sonic boom research provided critical insights. Charles Boccadoro's leadership guided the overall effort. Peter Cohen's persistence kept NASA engaged. Mark Gustafson represented DARPA's interests. Ken Plotkin's boom propagation models predicted what should happen. The list goes on, encompassing dozens of engineers, technicians, pilots, and researchers whose individual contributions combined to create success. Their achievement stands as a testament to what dedicated professionals can accomplish when pursuing a clear technical goal with adequate support. The SSBD project cost several $1 million, modest by aerospace standards. It took about 2 years from contract award to successful demonstration flights. It produced definitive proof of boom shaping that has influenced a generation of supersonic research. By any measure, it was a success. As we look to the future of aviation, supersonic flight will likely play an expanding role. The technology is mature. The physics is understood. The engineering challenges, while significant, are solvable. Environmental concerns can be addressed through advanced propulsion and sustainable fuels, and the sonic boom problem that once seemed insurmountable now appears manageable through careful shaping techniques validated by projects like SSBD. Perhaps someday, when supersonic airliners routinely cross continents and passengers take for granted what was impossible for their grandparents, people will look back at that strange pelican-nosed F-5E and recognize it as a pivotal moment. The shaped sonic boom demonstrator didn't just prove a theory or collect data. It changed what was possible. It opened doors that had been closed for half a century, and it stands as a reminder that in aerospace, as in all fields, patient effort toward ambitious goals can transform seemingly impossible dreams into everyday reality. Epilogue: The Thunder Tamed. On a quiet morning at Edwards Air Force Base, if you could stand on Rogers Dry Lake and imagine the scene from August 2003, you might visualize Roy Martin in the cockpit of that modified F-5E, accelerating through the sound barrier, the aircraft's unusual silhouette slicing through the high desert air. Below him, 42 sensors waited, arrayed along miles of desert floor. Behind him, an F-15B probed his shockwaves. Above, a sailplane glided silently in position. In the control room, engineers watched data streams, hoping to see confirmation of predictions made by decades-old theories. And then, the shaped boom arrived. Not with the sharp crack of a conventional sonic boom, but with a different signature. A gentler pressure profile that validated years of work and opened new futures. That moment represents more than just a successful test flight. It represents the culmination of efforts that began when engineers first realized sonic booms were a problem that might be solved, continued through decades of theoretical work and computational modeling, and culminated in proving that theory could become reality. The thunder has been tamed, or at least we now know how to tame it. The path from that knowledge to widespread practical applications still lies ahead, but the essential barrier has been overcome. Sonic booms need not be loud. Aircraft need not be relegated to flying over oceans and deserts. The dream of routine supersonic flight across continents, deferred for half a century, is becoming achievable. As we conclude this journey through the story of the shaped sonic boom demonstration, I want to leave you with this thought. The history of aerospace is filled with challenges that seemed impossible until dedicated individuals refused to accept impossibility. Breaking the sound barrier, flying to the moon, building reusable spacecraft. Each represented problems so daunting that many serious people believed they couldn't be solved, at least not in their lifetimes. The sonic boom problem was one of those challenges. For decades, it appeared insurmountable. But engineers and scientists kept working. They developed theories, refined models, conducted experiments, and eventually flew an aircraft that proved the theories correct. Now, as the X-59 prepares for flight and companies develop supersonic business jets, incorporating boom-shaping technology, we stand on the threshold of a new era in aviation, an era that the SSBD team helped make possible. So the next time you hear an aircraft overhead, or read news about supersonic flight programs, or wonder about the future of air travel, remember that Pelican-nosed F-5E and the team that flew it. Remember that solving difficult problems requires patience, expertise, collaboration, and willingness to keep trying even when success seems distant. And remember that the thunderous sonic boom, once thought to be an inescapable consequence of supersonic flight, turned out to be shapeable after all. The quest for quiet supersonic flight continues, building on foundations laid by the shaped sonic boom demonstration. As that quest progresses toward practical realization, we can appreciate the remarkable achievement of proving that shaped booms work in the real world, not just in equations and computer simulations. That proof changed everything. It transformed sonic boom minimization from speculative theory into demonstrated fact. And in doing so, it brought us one step closer to a future where supersonic flight becomes routine, practical, and accepted over land as well as water. Thank you for joining me on this exploration of the shaped sonic boom demonstration project. If you enjoyed this deep dive into aerospace history and technology, please like this video and subscribe to the Space Historian channel. There are so many more fascinating stories from aviation and spaceflight history waiting to be told. Stories of innovation, perseverance, and breakthroughs that changed our world. I look forward to sharing them with you. Until next time, keep looking up, keep learning, and keep marveling at what human ingenuity can achieve when we dare to tackle the impossible.